Okay, hi everybody, and welcome back. So we have just a few more things to talk about in Chapter 17, and then we'll move on. I will post your Chapter 18 study guide later today. I'm sorry, I've not gotten quite to that yet. So last time we were talking about decarboxylation. Actually, we were talking about using this familiar beta keto ester to do a really efficient and easy enolate alkylation reaction. And the point was because the proton in between the two carbons, between the two carbonyls, is especially acidic with pKa 13, that we could quantitatively generate an enolate, and then in a second step we could introduce some alkyl halide, and that would allow us to make the new carbon-carbon bond with the alpha carbon without having to worry that any leftover ethoxide might react with our alkyl halide. Because by the time we introduce the alkyl halide, all of the ethoxide has been consumed in removing this proton. And then we said that you can convert this starting material, you can convert the product of this step using acid in water and heat to give you this ketone product, and where this portion of the ketone, or this portion of our product ends up here. And then where does this portion go? Well, we lose part of it as ethanol and then part of it as CO2. And remember, there were three things that happened here. First, you hydrolyze the ester, and that's a Chapter 16 reaction. Second, you do a decarboxylation reaction. And then third, you tautomerize from the enol back to the ketone. The key decarboxylation step was this one, where the proton of the carboxylic acid is already hydrogen bonding with the ketone oxygen on the beta carbon. And we said that what can happen is lone pairs on the oxygen remove the proton. We did this stepwise last time, but the way your text shows it, electrons here kick down to form a new pi bond, kicking off the alpha carbon with a negative charge on it as the enolate, though we can instead push arrows like this, and that gives us CO2, and then this enol, which is the less stable form of the molecule, which will rapidly tautomerize to the keto form. But the reason we can do a decarboxylation step is basically, if we were going to think about this happening stepwise, is basically the idea that this group here is a decent leaving group because the negative charge that's going to end up on the alpha carbon when it leaves is stabilized by resonance. So if we kick those electrons down and the portion in green leaves, the negatively charged carbon that negative charge on the alpha carbon can be delocalized via resonance. Okay? So when decarboxylation happens, it's because there's something attached. You first have to have something here that you can turn into a carboxylic acid. But once you have the acid, you need some group attached to the alpha carbon that can stabilize the negative charge that's going to be left behind on the alpha carbon when CO2 forms. Yeah?
So just to clarify, on like like at the very top, which is the dim blue, right? When you add that acid, where exactly does that extra proton go on the?
Okay, where does, when you add this acid?
Yeah.
Okay. Well, so the first thing that happens is that you hydrolyze the ester. That would involve protonating this carbonyl oxygen. Water attacks to give a tetrahedral intermediate. Proton transfer turns this into a good leaving group. Electrons kick down and kick off this group, and you have the acid, basically. There's some more proton transfers there. So this proton here, I guess I would say, comes from the acid. And then I guess that's the proton that's here in the enol. Is that sort of what you were asking?
Yeah.
Yeah, now when we tautomerize to get the product, water or some base removes this proton, and then we add another proton back on the alpha carbon. It's probably not the same proton by that point, but you can't tell them apart. So, all right, what else? So why did we talk about this, other than that it's a practically useful way to give you this methyl ketone? The answer is that nature uses decarboxylation all the time to make important messenger molecules. And it uses this same pattern where you have something attached to an alpha carbon that can stabilize a negative charge by resonance. All right? So let's talk for a few minutes about decarboxylation in nature. All right, so nature can take an amino acid starting material, and the amino acid I'm going to draw for you is called histidine. You don't need to memorize its structure, at least not yet. If you take biochem, they will make you, depending on how I'm feeling at the end of the semester, I will make you do it as well. And then by the third or fourth time you've had to do it, you'll actually remember them. There's an enzyme called, unsurprisingly, a decarboxylase. That's just the general enzyme family. And there's a cofactor called PLP. That stands for pyridoxal phosphate. We have seen that before, and I will draw it for you again in a little bit. This will cause CO2 to be removed from the molecule, and you'll be left behind with this molecule, which is called histamine. Make sure I got the right number of carbons. Yep. And of course, histamine is a signaling molecule that's involved in, degranulation of mast cells and the allergic response. And so if you're having allergies, you take antihistamines, which probably slow down the synthesis. I'm not sure actually if they slow down the synthesis of histamine or rather just block histamine from binding its receptor. We could look that up and find that out. But in any case, that's how your body takes an amino acid and turns it into another useful compound. And it's really beautifully efficient, right? Instead of inventing a whole other molecule to do this, you take an amino acid that you already have for other reasons and then repurpose it through a small reaction that dramatically changes the physical properties of the molecule. So how does this work? We're going to have to do something because if we did the decarboxylation now and we put a negative charge on that alpha carbon, it would not be stabilized by resonance. So we're going to have to do something, particularly to this nitrogen, to turn it into something that can stabilize the negative charge by resonance. So enter pyridoxal phosphate. We've drawn this before, and every time we do, it's kind of a pain. So I'm sorry. You have a positive formal charge on this nitrogen. You have this branching phosphorus group, and then here you have the business end of the molecule, at least at the beginning, which is an aldehyde. Okay? Aldehyde amino group. We're going to put those together and form an imine. Primary amino group and an aldehyde will undergo imine formation. That's chapter, can't remember. Somewhere, I think it's probably 15 or 14 or something like that. So I'm not going to show you that mechanism. We've done that before a couple of times, and you can go back and review that as needed. So I'm just going to draw the imine once it's formed. And hopefully, if it's okay, I'm going to abbreviate all of this as an R group. By making the imine, look at what we've done in comparison to what we did previously with our beta keto acid. I'm going to highlight the part in blue that's going to leave as CO2, and then the part in pink that's going to be left behind, noting that when CO2 kicks the pink portion off, the negative charge on that alpha carbon can be stabilized by resonance. Look at the same pattern here. Here is the, oh shoot, I forget what colors we used. In blue will be the that's not blue. In blue will be the CO2 that leaves. The negative charge will be left behind on this alpha carbon. And the question is there something adjacent to that alpha carbon that can stabilize a negative charge by resonance? And the answer is, if you had a negative charge here, look, it's adjacent to a double bond. So that is a situation where you could undergo resonance. So let's just try it out and see. The mechanism of decarboxylation is going to involve that negatively charged oxygen kicking its electrons down, kicking off the rest of the molecule, and at least at the beginning, we're going to put the negative charge on the alpha carbon. Okay, so let's draw, and this step will be irreversible because, of course, we're going to lose CO2. Once you've lost it, it gets dissolved in your blood and then exhaled out your lungs. I lost a methyl group there, which was not intentional. So here's what used to be our alpha carbon. Here's CO2 that has left. And notice, and I'm going to push arrows to demonstrate how we can delocalize this negative charge via resonance. Of course, you don't need arrows to convert one resonance structure into another because the electrons are not actually moving. That lone pair electrons on the alpha carbon are actually delocalized throughout this conjugated system and therefore stabilized so that it's not such a bad thing for CO2 to kick off the leaving group. All right. And if we wanted to, we could point out that lone pair electrons would be shared on these atoms and this atom and that atom. I'm going to erase these arrows now. I was just wanting to show you how we convert one resonance structure to the other. But remember, these are two different descriptions of the same molecule. And it's this delocalization of that lone pair that makes it possible for this whole thing to be the leaving group. All right. Then what happens? Well, if we protonate what used to be the alpha carbon with some acid, either from solvent or from the enzyme, We've totally run out of space. That's okay. We will get the following as a product. Having protonated that alpha carbon, we no longer have to worry about stabilizing a negative charge by resonance. Then this is just an imine. Oops. That we can hydrolyze. And that, and I'm just going to draw the arrow right here. This is imine hydrolysis. And that will liberate pyridoxal phosphate, our cofactor, and will make histamine, where this portion is the R group that we abbreviated early on. Okay, so the idea of having a carbon that's alpha to a carboxylate group or carboxylic acid group, and that's adjacent to something that can stabilize a negative charge by resonance, sets you up nicely for a decarboxylation reaction. And this isn't the only amino acid this happens to. If this side chain group were a benzene ring with an OH, the decarboxylation would give us dopamine. Actually, it would need to be, so the nature takes the amino acid tyrosine, adds an extra OH group to it, then does the decarboxylation. You get dopamine. Serotonin, in the same way, starts with tryptophan. You do the decarboxylation and you get serotonin. So very powerful molecules made from fairly ordinary precursors, but using this method. Okay, anything you want to ask about that? Sure.
So PLP hydrolyzes hydrogen.
So we're going to hydrolyze the imine with water, and the enzyme is going to catalyze that. What I meant by that is that PLP is this portion of the molecule. When we hydrolyze the imine, this side is going to be an aldehyde again, and this side is going to be an amino group again. So we're going to regenerate this PLP molecule, and then that releases the amino portion of the molecule, which is okay, what else? Okay. And of course, well, yeah, anyway. So there's one more reaction we need to talk about in chapter 17. I do this because it generates a molecule that's synthetically useful, but we're not going to spend a huge amount of time on it or worry about the mechanism in a lot of detail. The reaction is called alpha halogenation of carbonyl compounds. And the idea is that we can take a ketone or an aldehyde and we can use Br2, and we need an acid to make this process happen. Usually the acid of choice is acetic acid because it can be both acid and solvent. The net effect, though, is to replace a carbon-hydrogen bond on the alpha carbon with a carbon-bromine bond. And of course, bromine is useful now because this is a good leaving group. So we can do some of the same things we've been doing all along with good leaving groups, reactions that we learned in 351. Briefly, the mechanism of the reaction involves first protonating the carbonyl oxygen. And that process of making this oxonium ion then makes it easy for the conjugate base of our acid to remove the proton that's alpha to the carbonyl, and that generates the enol intermediate. Okay, and of course we could draw a resonance structure of the enol that would look like this with a negative charge on the alpha carbon. So at that stage, it's no surprise that when we introduce bromine as an electrophile, the alpha carbon, which is nucleophilic, can attack the bromine-bromine antibonding orbital and break the bromine-bromine bond. That step generates a new carbon-bromine bond, which is so much more stable than a bromine-bromine bond that this step is not reversible, and then we'll regenerate our acid using the conjugate base perhaps to give us the carbonyl compound. I believe your text shows Br minus doing this. I really don't like that because Br minus is not a good base. So we're going to be agnostic about what this base is, and yeah. So this is a good way to install a leaving group on a carbon alpha to a carbonyl. Now, and look at what this does. This is interesting because normally we've been thinking about alpha carbons as being nucleophiles, right? We've used enolates as nucleophiles before. In fact, even here we're using the alpha carbon as a nucleophile, but as soon as we install that Br group, now that carbon becomes electrophilic, and we can do other things with it. Okay, so let me show you an example of some things you can do. Here is a ketone. I think somebody asked during the first hour, you know, what about less substituted versus more substituted enols? And I really don't think your text gets into that at all, so we won't either. Presumably you would get the more substituted enol because these first few steps are equilibrium steps, but we're not going to belabor that point. So let's install the alpha bromo group. I will sometimes abbreviate acetic acid like that. That's going to first make the enol, which will then react on the alpha carbon to give you this alpha bromo ketone. Now let's think of all the things we've done in the past with good leaving groups. So from 351, what about an SN2 reaction with a good nucleophile? For example, if we wanted to use this negatively charged thiol, it's called a thiolate, we could do the SN2 reaction where electrons here would attack from behind, attack the carbon-bromine antibonding orbital, and break the carbon-bromine bond to give you a new carbon-sulfur bond. That would be a substitution reaction, right? In contrast, we could do an elimination reaction. Now, if you were going to choose a base to do the elimination reaction, what would you pick? You're saying tert-butoxide, that's your go-to base for shutting down the potential competing substitution reaction. And I like that, and I think that would work just fine. That would give you, as a product, this molecule, which went from being an alpha bromoketone to be an alpha beta unsaturated carbonyl compound. And we're going to pay attention to that because we've seen this as starting material before in our previous unit leading up to exam 1. One thing I do want to say, though, about this elimination reaction is that your text presents an entirely different set of conditions. From the text, the choice of base is lithium carbonate, that's your base, and then lithium bromide is some kind of additive. And your text never explains what lithium bromide is, or what it does. Carbonate looks like this, and it has its conjugate acid bicarbonate has a pKa such that it's a decent base for doing this elimination reaction. Why does your text do this instead of tert butoxide? I don't know. And I have a hypothesis, but I'm going to be fine with you using, say, tert butoxide to do this reaction. One thing to understand about your text is the author, Professor Janice Smith, is a classically trained synthetic organic chemist, and she trained in the lab of Nobel laureate Professor E.J. Corey at Harvard, and he won the Nobel Prize for making very, very complicated molecules using organic synthesis. And a lot of the brilliant synthetic chemists that are around today were trained in his lab. Synthetic chemists, when they go to do a reaction, they often consult the literature to see if somebody's done something similar before. And if they have, why reinvent the wheel? You try to follow their conditions and tweak them as necessary. And so likely the fact that Professor Smith is presenting these conditions for you to do the elimination reaction reflect that this is what somebody has actually done and it works. It doesn't necessarily exclude other possibilities, but in many cases, synthetic chemists have the attitude that if the reaction works and is high yielding and fast, then why try to do something else? So, but I'm never going to give you a situation where I say, which of the following reagents carries out this reaction, and you have to choose between this or that, because the answer is, for our purposes, they both would work. Now, in practice, if one works better than the other for some mysterious reason that we don't understand, that's okay. There's a lot in chemistry we don't know. All right. What can we do with alpha-beta unsaturated carbonyl compounds? And this is just to get you thinking synthetically. Well, with cuprates, we've installed R groups at the beta carbon. With organolithiums and Grignards, we've installed alkyl groups, R groups, at the carbonyl carbon. So those are two sort of wildly different, well, not, I guess, wildly different, that might be an exaggeration, but quite different products, just based on same starting material, different reagent. We could use lithium aluminum hydride or perhaps sodium borohydride to reduce the ketone to an alcohol. I suppose if we wanted, we could use hydrogen and palladium on carbon to reduce the alkene to the alkane, and if you use the right conditions, you don't worry about reducing the carbonyl. But now that I think about it, that's sort of a boneheaded way to get right back to our starting material. So we'll just pretend that we didn't think of that. Okay. Questions? All right. So we're going to move on to chapter 18. And in doing so, I'm mindful of the fact that you're going to feel like the world has gotten a lot more complicated. And that's okay. From time to time, I encounter students out and about in the community. I met one at Walmart the other night, and his significant other was with him, and I apologized to her for the pain that I had caused their relationship, just assuming that there had been some. And I know this from experience because a gazillion years ago in I think it was fall semester of 2000. I was newly back from the mission, and I was dating Amber, who I'm now married to. But we didn't know that was totally going to happen back then. And I was taking OChem from Professor Savage here, Dr. Savage, who's still here. I'm sorry, he and I are PhD brothers, actually. We got our PhD from the same guy, but years apart. Any dad story involves extraneous, irrelevant details, so just go with it, okay? Anyway, we were driving around Provo, and something was wrong, and I kept thinking, are we about to break up? Because she didn't seem happy, and in sort of sadness, she said, don't you even want to spend more time with me? I apparently was spending a lot of time on my homework. In fact, I think I would study clear till 9 or 9:30. I'd walk from more extraneous details. Sparks 2, which is still there and I think is still a dump. And I don't remember, but it was one facing the parking lot on the first floor. So,
Wow.
yeah. Do you? Okay. I have. It was okay. I mean, I had roommates that were too in love to clean up on whatever on one St. Patrick's Day. One of the roommates made corned beef and cabbage, which he and his girlfriend only sort of ate, and then they left it in the sink for at least a week afterwards. So be good humans is the moral of the story. Anyway, so yes, if you're in that apartment, I have personally declogged the sink with a plunger before. Anyway, so I wondered if we were breaking up. Amber said, "Do you want to spend any time with me?" And my pattern had been to study, then walk from Sparks 2 to King Henry, and spend 5 minutes with her, kiss her goodnight, and then go back home. And naturally, this was not the relationship she had envisioned. So she said, "Don't you want to spend more time with me?" And I said, "Well, on Wednesdays I could," which was not the right answer, as you can imagine. And so I learned through sad experience to adjust my priorities. I started studying over at her house so that I could study and be near her, which was good. But the whole conflict about time spent studying versus relationship continued even into our marriage. And things finally got great in grad school when there wasn't any homework anymore. It was just doing stuff in the lab. So anyway, I've sort of been where you are, and I apologize for the strain I'm causing on your most cherished relationships. It will get better, and feel free to blow off OChem in the interest of saving a relationship. Can you get that in writing? Yes. Will I give you points, free points for having other things going on? No. All right. Well. So the world's going to get a bit more complicated, and I think it probably already is, because we started with this carbonyl compound, say acetone, and we pointed out that if hydroxide attacks the carbonyl carbon, we get the ketone hydrate. That was something we did early on in the first unit, and for many of our purposes, the hydrate is sort of a dead end synthetically. There's not really a lot we do with it. And so this is just sort of a side equilibrium that goes on, but is mostly inconsequential. However, if hydroxide attacks instead the alpha proton, we've said that we can generate the enolate as an intermediate, though we only generate a very small amount of it. We said something like less than 0.01% enolate and greater than 99% starting material. We also said that the enolate can get protonated on the alpha carbon to give you the enol, though we've said the enol is less stable than the keto form, so most of your material is going to be here. We said that the small amount of enolate that's present is enough to do chemistry if we have some electrophile that can draw off material from enol, hydrate, and ketone down to whatever the product is. And in general, that electrophile so far has been, let's use some alkyl halide. However, we've ignored something. And that is that the ketone is itself an electrophile. Right? And in this equilibrium, the ketone is present with the enolate. Now, how do ketones react as electrophiles? Well, we've had a nucleophile attack the carbonyl carbon to give us a tetrahedral intermediate, where we form a new bond between carbon and nucleophile. And if the nucleophile isn't a good leaving group, we're sort of stuck there until aqueous workup, wherein we generate the alcohol. Okay, we've done this with all kinds of nucleophiles. In fact, hydrate formation is an example of just this sort of thing. So the question we should ask is, what if the nucleophile is an enolate? And that's going to look complicated, but I want you to see it as a manifestation of something we've already done. Here is the enolate as a nucleophile. I'm going to show the resonance structure of the enolate where the negative charge is on the alpha carbon. So here's your 0.01% of enolate. Here's the majority of your material as ketone starting material. Just like we did here, nucleophile attacks electrophile to get a tetrahedral intermediate. Exact same arrows. What's the product going to look like? Well, just like we did above, we would first have a negatively charged oxygen here. The new bond that we made is going to be here, and that bond is going to be between the alpha carbon of the enolate and then the carbon of my tetrahedral intermediate. So here's the alpha carbon of my enolate. Here is the carbonyl carbon, what used to be a carbonyl carbon of my tetrahedral intermediate. And then, of course, I can pick up a proton from water or some other source to give me this product in which I have connected two equivalents of my ketone together. One is an enolate and one is the ketone. This portion of the molecule was the electrophile, and this portion of the molecule was the nucleophile. This portion was the enolate. This portion was the carbonyl compound. Okay, and that reaction, starting from ketone and enolate, has a name, and it's called the Aldol reaction. And it's called that because I think it was originally discovered with aldehydes, and the product was an aldehyde here and an alcohol there. But the name has stuck for all kinds of different carbonyl compounds. All right. Questions so far about that? Yeah, go ahead.
How do we know that the nucleophile will attack a carbonyl compound versus a non?
How do we know that the enolate will attack the carbonyl versus the alpha proton?
Yeah.
Okay. What if the enolate removed the alpha proton? You would turn this enolate back into the ketone and that ketone into an enolate. So sure, that happens all the time. Yeah. Yeah. Oh, I'm sorry. Go here first and then there.
Can you do like the 6-membered ring deal down at the bottom?
Could you do the 6-membered ring deal down at the bottom? Would this product actually involve an intramolecular hydrogen bond? Probably. Somebody in the first hour asked, okay, well, that looks like something we did a decarboxylation reaction with. And I said, yes, except there's no oxygen here, and there's no group that could stabilize the resulting negative charge here via resonance. So yeah, you do have probably an intramolecular hydrogen bond there, though it's not, it may not be, I mean, it doesn't set you up for decarboxylation. Yeah, go ahead.
Are there ways to drive this reaction forward?
Are there ways to drive this reaction forward? Yeah, this is a good question because remember, we only start out with a very small amount of enolate. So I've shown you the mechanism. I'm trying to be organized here. And I'm showing you here the analogy between what we did before and what we're seeing now. But let's imagine we're just going to alter our equilibrium, bringing these two things together. They're going to be in equilibrium. Each of these steps of the mechanism is an equilibrium step. So those starting materials, the enolate and the ketone, are going to be in equilibrium with this product. And what that means is that even though I only have a very small amount of enolate, as soon as it reacts with a ketone, you generate this. That's going to pull more starting material over to enolate. and so on until the reaction ends. And the thing that's going to drive it forward is if the product is more stable than the starting materials. Good. Other questions? Yeah.
Does this continue in like a chain sort of fashion where like another one hooks onto the ketone and just keeps going?
Could this continue on in a chain fashion sort of iteratively? In other words, could another enolate find this ketone and attack? Yeah, that sounds reasonable. And there may be a challenge problem or two in the text which will have you think of that, but it'll be in a mechanistic context. Instead of saying predict what happens, they will say tell me how this happened. And so as long as you would be able to come up with that hypothesis, you'd be fine. I wouldn't expect you to predict that. Yeah. I saw another hand, sorry. Somebody else? No? Yes? Yes, thank you.
So then, is this going to be more of like a substitution or an addition?
Yeah, what kind of reaction is this? It's an addition reaction because the enolate is adding to the carbonyl. Though sometimes it's called a condensation reaction because you're condensing two of the same molecules together into one product. So that's why the title of chapter 18 is Carbonyl Condensation Reactions. So one thing that I want you to pay attention to is structural patterns in the products. Get used to seeing particular structural patterns in products and connecting them to starting materials. What am I talking about? Well, the product of the Aldol reaction is a beta-hydroxy carbonyl compound. Why am I calling it beta-hydroxy? Because in my new molecule, I have an OH group on the beta carbon relative to my carbonyl. So when you see a beta-hydroxy carbonyl compound, right away you should be thinking, I could have gotten this portion of the molecule from a carbonyl compound, and I could have gotten this portion of the molecule from an enolate. And that would have been formed by making this bond between alpha and beta carbons. Later on, when we get to metabolism, we're going to show you that fructose itself is an example of a beta-hydroxycarbonyl compound, and we're going to use the backwards reaction. This is an equilibrium. We're going to use the backwards reaction to break apart fructose into two different parts. Doing so is called a retro-Aldol reaction, and we can push arrows for that another time. But looking at this product and recognizing it as an Aldol product is going to be really useful to you as you're thinking about synthesis questions. Okay, now I said it was going to get worse, and there's still more. And that is that experimentally, people have observed that this Aldol product often goes on to form not the beta-hydroxycarbonyl compound, but now the alpha-beta unsaturated, meaning a double bond between alpha and beta carbons, an alpha-beta unsaturated carbonyl compound. And this is a dehydration reaction because you're removing one of the protons on the alpha carbon and the OH group. Nevertheless, so you need to get used to looking at alpha-beta unsaturated carbonyl compounds and think that portion in orange came from my electrophile and this portion in blue came from my enolate. And this is tough because this is one step further removed. The oxygen's gone now, so it's not as easy to see, oh, that we could have got that from addition of an enolate to a ketone. How does that happen mechanistically? I can show you that now. It proceeds via an elimination reaction. but it's not an E2 reaction, in part because the thing that would have to leave is OH minus, and that's not a great leaving group, and we're under basic conditions, so there's no protonating it to form a better leaving group. But E1 isn't an option because OH minus isn't going to leave to give a carbocation. So instead, the mechanism is a new version of elimination that you haven't seen before, though it should make a lot of sense. The first thing that happens that's fast is that some of your base in solution removes a proton to make an enolate here at the alpha carbon. Now, if it were an E2 reaction, instead of having these electrons go on the alpha carbon where they're stabilized by resonance, we would have simply had these electrons kick down and OH minus leaves. But it turns out OH minus is not a good enough leaving group to leave until we have the negative charge on the alpha carbon. So this deprotonation step is fast. The following step of elimination of the OH group is slow. These electrons kick down to form the pi bond, OH leaves, and that gives us our alpha beta unsaturated carbonyl compound. Because this is the slow step, it is the rate determining step. Because there's only one molecule in the rate determining step, it's an E1 reaction, but it's not the classical kind where we form a carbocation. So the chemists tack on Cb for conjugate base, meaning that first you make the conjugate base of your beta hydroxy ketone, and then you do the slow elimination reaction. All right, so what I've told you so far is that we can observe either of these, the beta hydroxy carbonyl compound or the alpha beta unsaturated carbonyl compound, as products of the Aldol reaction. Your text doesn't really give you a way to say which one to expect. In reality, because this is an equilibrium step, it is going to depend on the relative stabilities of the products, the hydroxy ketone versus the alpha beta unsaturated ketone. And so sometimes if one is more stable than the other, you might observe one being the major product. I'm going to accept either as options. I'm not going to give you a question where which of these is the product and there are both of those options and you have to pick one. And if I did that, you can come complain to me after the fact and I will give you credit for the answer that's correct, all right? Yeah.
So the dehydration that only occurs during basic solutions?
The dehydration, does that only occur under basic solutions? Well, the Aldol reaction is done under basic conditions. Yeah. Presumably, if you made this, you could use any other dehydration method after the fact to get it to go. I saw another hand. No? Yes?
I was just going to ask, so how does OH act as a leaving group? I thought OH is a poor leaving group.
OH is a poor leaving group relative to a lot of other things. Recall, though, that in hydrate formation, we've gone back to the starting material by having one negatively charged oxygen kick off another. And so the idea is that this enolate is unstable enough and reactive enough that it's fine and, in fact, downhill in energy for the OH group to leave. Okay. So I'm going to give you a problem that is difficult, and I want you to think backwards and show me what the starting material would have been. What I'm going to draw is, it's a six-membered ring. So now the little SpongeBobs in your head are running around, filing through files, throwing them everywhere, and things are on fire. This is an Aldol product. I want you to show me what the starting material would have been for the Aldol reaction. Just as a hint, you're going to need to identify alpha and beta carbons. And then as you move along, you're going to have a question because the starting material you generate is going to have more than one kind of alpha proton. And you're going to be troubled by which enolate gets formed. And the thing to remember is that the reaction all the way to products is in equilibrium. So actually, the stability of the enolate doesn't matter anymore, only the stability of the products. The reason enolate stability mattered before when we were alkylating enolates is because the alkylation step was irreversible. But if formation of products is reversible, then the only thing that matters is product stability, and this happens to be the most stable one. So, show me the starting material, show me the mechanism, we'll talk on Friday.